You are especially welcome to this lecture video. In this lecture video, we shall consider simple linear regression in Excel using the data analysis package. In particular, we shall fit a simple linear regression model in Excel. We shall estimate the parameters of the model and test for statistical significance. So this is an aspect of statistics considered as inferential statistics or statistical inference. And then we have a question here. The question says the following data set gives the weight measured in kilo and the height measured in centimeters CMS for a random sample of 83 patients in a doctor's clinic. And we're asked to estimate the regression model for the data using the weight as the response variable, also called the dependent variable. And then the height is the explanatory variable or the predictor variable or the independent variable. Then the B part is for us to investigate statistically if the height is a significant predictor of the weight. And then we give reason to justify our answer. All right. So here is the data set. So we could see the height, which is X, the independent or explanatory variable. And here is Y, which is the weight. And of course, the weight or Y here represent the dependent or the response variable, which is the weight. So we're using the height to predict the weight if we have established the relationship between the weight and the height. So the first task is always to establish or estimate the relationship between the dependent and the independent variable. And if the relationship truly exists, then we can go further to investigate whether the predictor variable can significantly predict the response or dependent variable. So again, we want to use the data analysis package. So the first task is to go to the top icons. Then you click on data. Now, when you check at the top left-hand corner, you will not see the data analysis package, which is to say it has not been installed in the current version of Excel you are using. So in any version of Excel that you're using in your PC, all you need to do is to get the package installed first. So to get this clearly done, you need to go to the top left corner. You will see File. So at the top left corner, you see File, then click on that file. Then move down to the last icon in the drop-down menu. You will see Options. Click on that option. So from this option, what next? Move down again from among these drop-down menu, go to the last icon, which the second to the last icon rather, which is add-ins. So click on this add-in. From add-in, proceed to Go at the bottom. Click on Go. And then tick this analysis toolpack. If you're also happy with Solver in Excel, which could be used for other purposes, you can tick. And then you could say OK. Now you could see it blinking in this blue color. So it means it's coming up. Now you could see the data analysis and then the solver packages that you have installed in the version of Excel you are using in your PC. So it's very clear now. Whether you're using a desktop or a laptop, you could see it at the top right corner. Data analysis and then the solver. So now we want to perform the analysis. Click on this data analysis. And then you proceed to what you want. It's bringing it out. It's loading. So we could see we have all of this. But what you want is actually regression. You want to perform a simple linear regression analysis. So we move down to regression. So click on regression and then tell Excel OK. Then we need to impute the Y range and the X range. The Y range will be your dependent or response variable, which is the weight. So highlight the weight column. So we have all the observations for the weight, including the variable name weight. Then the next one is the X. We want to impute the X range. So we have height. So you impute the height. To do this, you highlight all the observations, including the variable name, if you are happy with that. And then next, labels represent the first row. Remember, in Excel spreadsheet, we have the rows and the columns. Now, these are the rows representing cases entered in the Excel spreadsheet, while you could see the columns, column A, column B, C, D, E, and so on. While the rows are represented with numbers. The columns are represented using alphabets, while the rows are represented using numbers. So we have row 1, row 2, row 3, row 4, and so on. So now you could see that height here is in the first row. Weight is also in the first row. So that is the reason why I tell Excel that my first row represents the variable names, which are the labels. But if that is not the case, then untick this label. But because this is the case here, so I have to tick. But assuming I do not include the variable name, then there is no point ticking this box. All right, if you are not happy with the constant, that is, you have a model without an intercept, then you should tick this box to show that there should be no constant. You only need the coefficient of the predictor variable, and then you estimate the parameter of the intercept. That is, the intercept as a parameter is estimated to be 0. But where you do not want the intercept to be 0, then you have to untick this. So untick this to show that your intercept should not be 0. It's different from 0. All right. The confidence level, yes, by default is 95% confidence level. But if you're not happy with this, maybe you want to impute, for instance, 99%, you can enter manually. If you're happy with the 95, you could leave it by default and it will be 95% confidence level. So this is to say that you are 95% confident that your estimates actually fall within the range you want. And you are just 5% not sure. So that's it. Now, where do you want the result to be? But before then, you also want to double check. If you want to include further analysis, like the residuals, the standardized residuals, the residual plots, line plots, and of course, to carry out normality test. So in this case, you check for the normal probability and the normal probability plots in particular. Then you could tick this box. But if you don't want that, then untick. For now, we are not testing for normality, whether the data set follow normal distribution or do not follow normal distribution. If we want to do that, we can as well perform that test using the Kolmogorov-Smirnov test, or we could use also the Shapiro-Wilk test to test for normality, in which the null hypothesis will say that the data set follow normal distribution. And then the alternative hypothesis will say that the data set do not follow normal distribution. Then that will be based on the result you will obtain. That is the output of the analysis. But in this case, we're just performing a simple linear regression model. All right. So what do we do? Now, I'll take this because I want the result to be in the same spreadsheet here. So let's assume I want my result somewhere here. So I have to click here in this box, rectangular box. Then I tell Excel that here is where I want my result to be. And then I could say, okay. So you could see clearly Excel have given us the regression output. So we have the regression output. You could see the coefficients of the model. You could see the sum of square, the mean square, the F value. We could also see the significant F. Depending on the software you're using. For the case of Excel, Excel will return the p-value as significant value. In this ANOVA, that is the analysis of variance table. Then in the estimate of coefficients, it will be recorded as the p-value. The p-value is the probability of rejecting the null hypothesis when it is true. And of course, that has to do with accepting the null hypothesis, the alternative hypothesis, when it is false. And of course, in performing this regression, our aim is to reject the null hypothesis and accept the alternative hypothesis only if it is true based on the justification that could be obtained from the table. So from this analysis, which you could see here, we have the multiple R here. We could see the R square. We could see the adjusted R square, the standard error, and the observation. Number of observation is 83. Then, of course, this also could represent the correlation. For instance, if you want to verify the correlation, you could go to correlate. For instance, this correlation. We want to obtain the correlation. So this is the way to obtain it in Excel. It's already done using the package, but we want to do it using the inbuilt. So you have correlate. Correl, C-O-R-R-E-L. Then in parentheses, you have this observation from the first to the last. In the first instance, comma, and then you go to the second variable. Close the bracket, and then enter. So you could see that the result is the same. This result here is the same result as this. This and this are the same. So this is the correlation. So we can say that it is a moderate positive correlation. Assuming the correlation is negative, then we can say that the two variables are not moving in the same direction. When one increases, the other one decreases. But in this case, we can see that an increase in height could also result to a corresponding increase in the weight of the patients. That is for the correlation. But the correlation here does not imply causation. It's just an estimate of the kind of relationship. You want to know the relationship. Is it positive or negative? Is it a strong or a weak relationship? So the correlation determines the strength of the relationship. So you could confirm that truly the correlation is not zero. If the correlation coefficient is zero, then there is no relationship or there is no significant relationship. If we go further to test for the significance of the relationship, then we could say there is no significant relationship or there is no relationship at all between the height and the weight of the patients. That is if the correlation coefficient is zero or has a value that is very close to zero. So it will be negligible in this case. But from what we've got, we have over 50% as the value here. If you want to put it in percentage, you go to percent here. And of course, you could see approximately 51%. So there exists a moderate positive correlation or relationship between the weight and the height of patients in the doctor's clinic. That aspect is sorted. Now we'll move on to the main aspect of this analysis. I could highlight this. And of course, I might even color it if we want. Let me use blue, for instance. So now we look at the intercept. These are the coefficients. So if you want to put this in the normal form, that is this analysis, we have the coefficients as minus 45.37. This is the coefficient representing the intercept or the constant. So this is, by simplicity, the constant. So we have minus 45.37, and then the coefficient of the height is 0.63699. If you want to take it to 2 decimal places, this will be 0.64. So the equation will be y is equal to minus 45.37 plus what again? Now, instead of writing y, let's put it as the weight in kg will be equal to minus 45.37 plus the height measured in cms. But we need to include the coefficient of the height. So what is the coefficient? The coefficient is this value, 0.64, approximately to 2 decimal places, times the height. We assume that it is error-free, so the expected value of the error term or the random disturbance is 0. So now we have this, and I could make this bigger so you could see it more clearly. So this is what we obtain. Let me color it. So we have the weight is equal to minus 45.37 plus 0.64 times the height in this case. And from this relationship, we can be able to predict the weight of any patient in the doctor's clinic if we know the height of the patient. So long as we know the height of the patient, in the doctor's clinic, we can predict the corresponding weight of that patient. And of course, the reason why we double check for the correlation is to actually investigate if there exists a relationship between the two variables or not, in order to avoid fitting a spurious regression. All right. For the significant aspect now, we'll move to test of hypothesis. We want to perform statistical hypothesis. So the hypothesis in this case, we have HO. HO is the null hypothesis. And the null hypothesis is saying that height is not significant. And the coefficient of height here, we could use B, for instance, beta, to represent the coefficient. We could use small case letter b. So we say beta is equals to 0, which is the coefficient of the height. This value, let's assume that this is beta. Then we now have versus. H1, which is the alternative hypothesis. So the alternative hypothesis is saying that beta is different from 0. It's not equal to 0. While the alternative hypothesis is opposing the null hypothesis. The null hypothesis is saying that beta is 0. Now, let me highlight and bold it again so it will appear more clearly. All right, so from what we can see here, this is the hypothesis tested. We have that HO which is the null hypothesis, saying that the coefficient of height is 0, while the alternative hypothesis is saying that the coefficient of height is different from 0. So if the coefficient of height is 0, then that means 0 times height will be 0. So it means height is contributing nothing to the model. But if the coefficient of height is different from 0, then of course it could be contributing, whether positively or negatively, to this linear statistical model. And of course, from what we could see here, you could see that the p-value, now we have a benchmark. We consider p-value greater than 0.05 or p-value less than 0.05. Again, let me bold this and make it look bigger. Could also color it if I want. Use this. So now in testing this hypothesis, we're also looking at this p-value. The p-value could give you an immediate decision. If the p-value is less than 0.05, then we can say that the predictor variable height is statistically significant. So we can reject the null hypothesis and accept the alternative hypothesis at 5% significant level. Whereas if the p-value is greater or equal to 0.05, then we cannot reject the null hypothesis HU in favor of the alternative hypothesis. And we will conclude that the data set do not provide sufficient statistical evidence to reject the null hypothesis at 5% significance level. But in this case, we can see clearly that the p-value here is by far less than 0.005. This value you have here, if you want to know the actual value that you have here, then you could even round this figure, round this figure. Let's assume you are rounding to 4 decimal places. So you can see we have 0.00000 until about 7 zeros before you now have 6, 3, 7, 5, E, and so on. So you could see this also in numerical form, where, for instance, you go to this, if you want to represent this now, or reduce the decimal. Rather, we could take the option of reducing the decimal. You could simply go to this point. You are reducing the decimal. You could keep reducing the decimal if you want. If you want to increase it, you take this option. It will increase the decimal back to normal as it is. So in this case, we could also go further here. For instance, you want to do something else. You could also consider, yes, this is a number. You put it in numerical form. If you want it to be in fractional form, you could also put that. You could go back over and over. Now you could see we have 0.00000 and so on, which is by far less than 0.05. So it is statistically significant in the model. In particular, we are saying that the height of the patient is statistically significant in the model. Therefore, the height of patients in this doctor's clinic is a significant predictor of the weight of the patients in the clinic. So we have drawn our conclusion based on our analysis. And then we could also see that the overall regression here, which is represented by the ANOVA, is also significant. So this is the F value. And of course, the F calculated will be greater than the F tabulated, the tabulated value for the F. And then from the significant F, which is the P value, you could also see that this is by far less than 0.05. Therefore, it is statistically significant. So the overall statistical model is also significant. And of course, we can draw our conclusion that the height of patients is statistically significant in the model at 5% significance level. Therefore, height is a significant predictor of the weight. So in terms of decision, we reject the null hypothesis in favor of the alternative hypothesis. Then the conclusion follows that height is a significant predictor of the weight at 5% significant level. All right, here ends the lecture in this video, and thank you so much for watching this video. Bye.